2, 1, 2. Hello, hello, ladies and gentlemen. Welcome to Goto 10. My name is Christopher Cameron. I work at Linköping Science Park, and as a part of my job at Linköping Science Park, I'm one of the hosts or the community managers here at Goto 10. But I see many familiar faces, but just a quick little note about Goto 10. It's run by the Internetstiftelsen, or as we say in English, the Internet Foundation. We do a lot of things. Please go to our websites and have a look what we do there. Actually, today we had a new publishing of the children and the internet, which is a big report we do every year. So there is a lot of good stuff in there. But if you are out here, live in Mjärdevi or work in Mjärdevi, please come and say hello to us. You can come here and work, you can bring your colleague, or you can do events like we do today. The event we do today is streamed on the internet. It's out there on YouTube, so we say hello to the people that are watching out there. And this is the series Tech Tuesday. Many of you have been here before. It is a collaboration between NIRA Dynamics, which is here today. It's Sectra, it's Ericsson, it is Combitech. And we are really happy that we do this every third week. This is the last one for 2025, but we will be back in 2026. And the schedule about when and where and who is going to speak on each day will be up on the website really shortly. So, but today, NIRA Dynamics and two young gentlemen would like to take us through a little journey on two wheels, isn't it? I think it's on 2 wheels, more or less, or maybe 4 actually, 4 wheels. So, but we will. I will let you over, and remember there. The sound, if you have questions, the guys up here will take your questions and repeat them, so it will go out to the stream on YouTube. And in the end, I will be back with the microphone and we will do a little Q&A. So, the floor is yours. Welcome.
Yes. Yeah, great. Now it works, I think. Sounds like it. So my name is Johan Petersson. I work as a product manager for NIRA Dynamics for our connected products. And with me I have Peter Sanders, who works as a product analyst. Yeah, and we will be talking about how we are enhancing traffic safety by using our connected vehicles. First, I will talk a little bit about what NIRA Dynamics is, so you get some context around that, and some introduction to traffic safety. And then Pete will take over and explain our new approach and some case studies that we've done. That was a really slow animation.
Yeah.
Yeah. So we're NIRA Dynamics. We were founded in 2001 as a spin-off from Linköping University by Fredrik, who is sitting here in the middle. Yeah. Our headquarters is here in Linköping, but we have a global presence in US, Brazil, Germany, China, Japan. And what we do is basically working with sensor fusion and software development, mainly for vehicles. We are owned today 100% by a company called Cariad, which is a daughter company of the Volkswagen. So we're basically 100% owned by the Volkswagen Group. And we have an annual turnover of around 30 million euros. Our sort of embedded softwares that our main products are today in more than 120 million cars, vehicles, where around 2 million are now connected, sending us data, which gives us new business cases. We are owned by the Volkswagen Group, but we do work with the entire market, or we try to work with the entire market. That would be good for us. But we have a large market share for our products, embedded products, within the automotive sector. So, yeah, this is we work with, we have basically 4 different products. We have the tire pressure indicator, which is our main sort of flagship. That's where we have a lot of different businesses around. We have loose wheel indicator, which I think is one of our, which is the product I like the best actually, but we don't have that in that many cars. It tells you when your wheel is loose, so increases safety by quite a bit. We have tire grip indicator, which measures friction, and tread wear indicator, which measures the tread wear. And this slide is a little bit redundant. And for our connected products, we use our tire grip indicator product that we have in the cars, where we collect friction, but we don't just collect friction, we also collect roughness data, temperature data, different types of, anything related to the road basically, where we then send that to like the OEM backend, we then, which is then forwarded to us. We don't have any direct connection to the car, but we do get the data from the cars through the OEM. From this we can build different types of maps, basically map layers, which can then turn into products. So we have 4 different connected products today: road surface alerts, road surface conditions, which are 2 sort of automotive products where we send alerts back to the car. So if you have a newer Volkswagen car, you can and you drive over a slippery spot, you can tell all other cars basically that this is a place where you should watch out. Road surface conditions is more towards autonomous driving, where we can give the autonomous vehicles more understanding about the road conditions. Road health is a product we offer municipalities and the road authorities, where they can use that to improve their planning for repayments and reconstructions of roads, reprioritize, hopefully optimizing their budget. And Winter Road Insights is our product for winter maintenance industries. So municipalities and road authorities that do winter maintenance use that product. Yeah, I'll skip this one, I think. We have today these are our biggest customers. So we work with Trafikverket, Swedish Transport Administration, the Dutch one, the Norwegian one, the Scotland one, and then we have some like Svevia and Mesta, which are the largest contractors in Sweden and Norway, and some cities. Again, here's a picture of road health where you pick up more, you get a map basically, and you also get information about the development rate of or deterioration rates of the roads. Whereas Winter Road Insights gives the winter maintenance crews information about, the biggest value there we have seen is within strategic support and measuring winter maintenance. So that's something that they've been missing, because before they have usually been going out and sort of guessing what to do. Now they can actually get feedback on their work. And this was quite a lot in the news like 2-3 weeks ago, where the infrastructure minister was out talking about this during a press conference. And we have another slow animation. So now we get into the traffic safety part. So today the products that we offer is Road Health and Winter Road Insights within the infrastructure domain. But we now also are building a product around traffic safety. This is going by automatic right now. What's happening? Pete?
Hey, oh,
Yeah. Yeah. So this is a definition or route traffic safety that where they say we found it on Wikipedia. It's referring to the methods and measures such as traffic calming to prevent road users from being killed or seriously injured. And we want to redefine it a little bit and say that it should be referring to the risk posed to the road users, non-road users, or surrounding property associated with the use of the road. Pete will get more into that later. I hope it stopped running automatic.
so
now.
do I. Yeah,
Yeah.
that's annoying, right?
Yeah. So today, data collection for road safety is basically road safety engineers being contracted by municipalities or road authorities, mostly. They will go out and it's flipped, right? What's happening? Can I turn it off somehow? I don't think so.
I don't think so. We'll have to live with
I'll
it.
talk faster. So one of the things they collect is accident reports. They use accidents, but there is a problem with accidents. They are quite sparse, and they don't really give a good statistical jump back. Yeah, they don't give really good statistical significance because they are quite rare if you look at the entire road network. And then we have something called infrastructure assessments, IRAP. Maybe you can mention that a little bit, Pete.
Yep. So this is the way that the traffic safety is managed in the United Kingdom, and essentially IRAP was designed as a way of sharing information about traffic safety between developed and developing countries. And the way that they did this was to generate an inventory of what the road looks like in any given condition. What's the speed limit? Is it close to a junction? Is that junction signalized? And so on. And to generate a risk score based on this. It has a number of benefits in that it's based on physical infrastructure that's already there on the ground, and clearly a number of drawbacks in that it's not based necessarily on dynamic vehicle-based data, and it's reliant on the models that were generated at its inception being valid still.
So they have that in some places, mainly in the UK, I think, right? Yeah. Then there is they collect speed measurements, and then also like how they try to collect as well how the traffic is interacting, cars versus pedestrians or bicyclists or anything moving around in the traffic, and they try to figure out what's going on there. Yeah, and they do this. They sort of. I'm not sure how they actually identify a site, but they do identify a site probably from. There was an accident here. Let's go investigate it.
It's mainly that, and there's
Yeah,
also
mainly that, right?
there's also some feedback from the public as well.
Yeah,
If they get enough complaints in a particular location, they'll send people out to have a look.
yeah, and then they have people going there and looking at it and making quite a subjective judgment of what's going on. They don't really use any input from drivers or vehicles, and they might also use like grad students, non-experts, to conduct this. And we also sometimes question if there are experts at all in the field. There are no standards, at least, and experts usually create standards. Yeah, and then sort of when they've detected something bad, they do some interventions, like limiting the speed, calming the speeds using speed bumps, for example. They do might need to improve the visibility for the drivers, some sort of signaling for crossings or whatever. or separation. Make sure that a car can't physically hit a bicyclist, for example, by putting up a wall or something. So, yeah, the limitations are that the historical accident data might not be up to date. I guess also that it's possible if they do an intervention, it's hard to measure afterwards. They have to wait to see if an accident occurs, for example. This was frustrating. Yeah, and data collection can be slow and costly because it involves people going out there watching. Yes, city like Linköping is quite a large place and many crossings, many things to investigate. So it would be quite expensive to just have a look at everything all the time. So not really scalable. And there is no adaptation to real-time conditions. You might want to include like weather data or whatever, rush hour or whatever. Yeah. And now Pete will start talking about our alternative approach.
That's right. It's one of those horrible things. You haven't been able to talk for the last 20 minutes and immediately need to clear your voice. So
you also have to focus on this one.
yeah, I know. This is very frustrating. I don't know what's caused this. My apologies. So one of the things that Johan spoke about is the limitations of the current methodology. And in my view, that is related primarily to our reliance on things that have already happened, namely accidents. But I don't think that this is really the goal of traffic safety. So we've redefined traffic safety here to be referring to the risk posed to the motorist, non-motorist, and property as a result of using the road. And this is quite different to the actual accident prevalence, okay? And the way that we can visualize this, is anybody here familiar with Dungeons and Dragons, D&D? Yes, brilliant, there's always one, two, fantastic. So these will be, these shapes will be quite familiar to you. They are different types of die. On the left we have a 20-sided dice, in the middle we have a 4-sided dice, and in the right we have a 6-sided dice. And if we are going to assign the property of 1 to being an accident has occurred, and any other number to be an accident isn't occurring, and provide any given road segment with one and only one of these dice, the question to you is, which one of these roads would you prefer to drive on? Does anyone want to take a guess? Which one would you prefer to drive on? The D4. Well done. Exactly. Because the chances of us obtaining... yes, the D20. That was right. Yeah, the D20, because the chances of us obtaining an accident on the D20 dice is a lot lower than the others. For example, in the middle it's 1 in 4. With the D20, it's 1 in 20. And we can see that quite clearly. So these are two images of the same stretch of road. They are actually from the opposite sides of the same stretch of road. And just judging by these images, which one of these stretches of road do you think is higher risk than the other one? Or are they the same? Are they higher, lower, or the same? Ignoring the car that's doing a time warp here for some reason. Yeah, I'd say they'd be about the same as well, right? There's no noticeable difference between these two stretches of road until we get into the accident data. So these points all represent an accident that's happened in the last 5 years, and they are all occurring, this is in the UK, so they're all occurring on the southwesterly stretch of this road. Now, if we were doing our traditional accident analysis and looking at this from an accident occurrence perspective, we would say that the southwesterly stretch of this road has a much higher accident propensity than the northeasterly side of this road, even though we know that can't be the case. They are ostensibly identical roads, right? And if there is a genuine difference between them, it's probably nothing that infrastructure can fix. So that raises the question, what other data sources do we have that can enable us to determine accident risk rather than accident propensity? And we often view that as an iceberg like this. So this is our definition of an unsafe road segment. It's one where you have a high prevalence of driver aids, speeding, low friction, some harsh maneuvers, and maybe the road signage isn't quite what it should be. So these are essentially the data types that we use in the development of our risk model. So for example, for an unsafe road segment, we have access to driver aids, ABS and electronic stability control, for example. And so we can gain ABS data for each 25-meter segment segment of pavement. And we aggregate these over some kind of observation period, typically 6 months, because we want to exclude winter conditions. There is a clear effect in the winter that accounts for the majority of road safety events, right? The next one would be speed. So we can also obtain some speed data from the vehicles. And we can generate a plot like the one which is shown on the screen at the moment, which is essentially a typical week. And again, these data will be observed over some kind of observation period. I believe this one is for 3 months. And we can do a couple of things with speed. So firstly, we can see if people are speeding. This is clearly the primary interest in this case. We want to know if people are driving too fast for the posted speed limit. But there's another thing we can do with speed as well, and it's not shown on this particular image, which is unfortunate, but we can analyze the difference between the speeds that people take during normal driving conditions and the speeds that people take during, for example, rush hour traffic. And from these pieces of information, we can do something similar to what Google Maps does. I don't know if you've ever been driving down the road and you come across the red bit, the horrid red bit, because you know you're going to be sat in traffic for a long time. And so we can essentially do something similar to this, where we can figure out where the red bits are by having a look at where there are periodically slow traffic compared to times when the traffic should be free-flowing. Oh, I've gone back. I need to go forwards. Here we go. Friction is another fairly clear one. Locations where we have low friction are probably going to be of interest to us. And friction is split into 2 parts. So you have the available friction, which is what we're looking at here, and utilized friction, which I'll get more onto in the next bit. But the available friction is something which is quite remarkable in that we can use the tire signals from the cars to estimate the friction, the maximum friction that could be generated between any car and any given road surface. And this is really important from a safety perspective, because what it allows us to do is to figure out what the worst case scenario friction is likely to be, or the reasonable worst case scenario. This is quite novel, new in the road space, in that the traditional way for assessing road friction would be to go out with some very expensive piece of equipment and make bespoke measurements. But often there is a disconnect between the measurements that are made and what the vehicle actually experiences. So we get the word straight from the horse's mouth here. The other side of the friction coin is the friction demand, or the utilized friction. And what's shown on the screen now is essentially a friction demand radial, where we can see the cluster of points for the direction and magnitude of the friction that was generated over a given road segment with some observation period, let's say 6 months again. So in this case, what we can essentially see is that the highest density region here is this one. And so we can do cluster analyses on these to figure out where our primary maneuver is and where our harsh maneuver is. We also have an additional data set for harsh braking, which I'll talk about in a second. And so in this case, forwards would be accelerating, backwards would be braking, to the right is turning right, and to the left is turning left. So this being in the UK, we can quite clearly see that this is a roundabout. People are turning to the right because we drive on the wrong side of the road. In addition to that, we do get harsh braking data. So harsh braking data is essentially a more detailed version of this data set, focusing on braking events only. And the harsh braking data have been shown in previous studies to correlate very well with accident risk. The last piece of the puzzle is road signs and markings. And we can do so much with road signs and markings that it falls off of the page, which is useful. And essentially what the vehicles do, if you've ever had one of those lane guidance systems, what that lane guidance system is doing is it's looking out for the bits of paint on the pavement. And it's saying, where am I relative to these bits of paint? But it can only do that if it can see these bits of paint. And some vehicles will see them, and some vehicles won't. And we can use that differential between the vehicles that have seen the markings and the vehicles that haven't seen the markings to estimate the quality of markings on the road. So in this example, we can see that on the right-hand side of this road, this is in Sweden now, that the visibility of the marking is less than optimal, and this would be picked up by our data analysis. Something similar with signs as well. Maybe you've been driving in your car and you suddenly see a 40 kilometers per hour sign come up. This is all based off of machine learning, which is in the vehicles. So how are we going to combine all of this data to manage risk? We have a lot of different variables and we need to figure out what to do with them. And so there are many approaches that you could use for this, and this is the one that we picked. We essentially created these spider graphs where each of the arms of the graph was a different feature on the road, one of the things that I've just talked about. And we assigned scores to each of these features based on the data, and you can essentially use the area covered by this set of lines, the area masked by that set of lines, to assign a risk score to the piece of road that you're interested in. And so essentially we can do that for each, whoops, oh, this is frustrating. It didn't populate properly. Yeah, essentially we can do this for each road segment that we're interested in. So this is just round the corner here from the science park. There might be the case, for example, that this roundabout entry is an E, this stretch of road is an A, and so on and so forth. And so we actually did this. We did this for a location close to where I grew up, in Wiltshire, in the UK. Apologies for the UK-centric nature of this. This was one of the data sets that we were putting together for a potential client, so it's been repurposed for today. Apologies. And this is Wiltshire, so it's roughly in the southwest of the UK, and it's we took what we call the 1 to 3 network. So this is everything except for very small residential streets, and it covers some meaningful area. And for each 25-meter segment of the Wiltshire road network, we carried out the procedure which I've just described. So we collected all of the data, we brought it together, we analyzed it, we produced a spider graphs, and we produced a risk score for each piece of the network. And the data that we were using was not everything that we could. You'll notice that the lines data has been exempt from this because it's a very new data set that we're still trialing. But we used, for example, the harsh braking rate, the ABS rate. Notice that these are presented as rates, so they are accounting for the trafficking rates as well. And one of the things which is really key about these data sets is the link between the two of them. So harsh braking data almost always, from any data supplier that you go to, we aren't the only ones who provide these type of data, but from any data supplier that you go to for harsh braking data, there will be some kind of friction or acceleration threshold that needs to be reached in order to trigger a harsh braking event. There's one very important and very specific case in which this fails, and that is the case where you have low friction availability on the road. If the road isn't giving you enough friction to reach that acceleration threshold, you nonetheless need to do a harsh braking maneuver, but you can't. So this is a fail unsafe scenario. But our data can account for that because we get the ABS activations back from the vehicle. So we can say, okay, we didn't measure any harsh braking here, but we did measure a lot of ABS. That tells us something quite important. The speed delta, and we also included within this a metric for the speed consistency to try and account for locations that were prone to traffic jams. A maneuver score was derived. Essentially, this is some kind of utilized friction parameter, and the hydroplaning rate and the available friction were also included in the data set. And these were the results. So this is every 25-meter subsegment of pavement for all of Wiltshire after it has been graded. And what can we see? Well, we call it the NRSI, the NIRA Road Safety Index. And we give it a letter grade from A to E. So all of the A's are really safe. You can go and drive on those and fear not, you should be all right. And all of the E's are not safe. And remember, we're talking about risk, not accident occurrence here. So if you're driving on an E, it's not guaranteed you're going to have an accident, but you know, you're rolling a D4 instead of a D20 in this case. And we can see something else. There are a few points which are E, but quite a lot that are A's. And the distribution of this is somewhat logarithmic. So the higher the risk score, the fewer observations you get, which is the way it should be. And for each of these locations, we produced one of these spider charts too. So, does anybody have any questions on that before I move on? Because the next bit is looking at some case studies. Yes. Please. Great question. So the question was, did we compare this with the actual accidents that occurred in this area? The answer is not yet. Not yet. But and the reason for that is because a lot of the data sets that we're using are very new. And when I say new, have become available in the last 6 months, okay? Especially the speed one. So we need to wait for the accident data to become available to do that analysis. But what we will be doing next year, before those data come out, is to look at the 24 and the 23 accident rates, because they tend to be similar-ish between years. Yeah, sorry, I think there was one more, was there? Nope, okay, great. Brilliant question, though. So what we'll do now is just take a look at some case studies, see how can we actually apply this. And the methodology for doing this was not particularly strenuous. It was me eyeballing the map and seeing if I could find anywhere interesting to present to you guys today. So this is one of the locations. This is remember, we drive on the wrong side of the road. So this is going into a roundabout close to a town called Marlborough. Marlborough is a very small town. It's probably only 1/10 the size of Linköping, something like this. And this is a particularly interesting location because firstly it has a very high safety index, D. But this exhibits exactly the behavior that I was talking about with the harsh braking data and the ABS data. And we can see that here. Our ABS rate is enormous. This is reported as events per 100,000 vehicles driven. So 530, call it, vehicles from 100,000 conducted an ABS maneuver here. That's very high. But there's no harsh brakings. And the reason for that is because the friction on that location is really low. And so you end up in a situation where if you slam on the brakes and you really want to do a harsh braking maneuver, you'll find that you don't have the friction available to do it. And so the ABS will trigger, and this is the explanation for what we're seeing here. On top of that, the maneuver score is quite high. We've got a 3 here out of 5. And the speed delta, it is low, but this isn't always a good thing. I mean, we're talking about a roundabout entry here, so you would expect people to be slowing down there. And this is what the site looks like from Google Maps. And we can see a few other things here. So if we were doing something more like a traditional traffic safety survey, where we can ask ourselves, where are the interactions? Well, there's a bus stop here. That's not ideal. I wonder if there's an appropriate sign to warn people that buses might be pulling out. And spoiler alert, there isn't. And we have, this is a huge giveaway to me. I'm a pavements guy by trade. So I look at this and I know what that is. I don't think you have this material in Sweden, but in the UK we use a lot of it. And that's called a high friction surfacing. And you'll notice that almost all of it is missing. So this isn't ideal. Also on top of this, there is a pedestrian footway which crosses the road here. And there's also a new built housing estate round to the left here. So here, to me, it's pretty clear what's going on.
Pete,
yes.
What happens when you wear off the high friction?
Ah, yeah, that's a good question. Yeah, well, so the high friction surfacing is a compound of two materials. It's calcined bauxite aggregate, which is very hard and very frictiony, provides a lot of friction, and that is embedded in an epoxy resin. And this herein lies the problem: is that when the aggregate starts to leave its matrix, what you're left with is smooth epoxy. So this isn't ideal. And it's also tends to be laid on top of materials that we already know have very low friction properties. And what is it that we're doing when we lay a load of epoxy over the road? We fill up all of the texture that was once there to provide friction to the cars. So essentially what you're left with when this removes is a very slippery, smooth surface. And so this is what I would do. We've identified we have a high ABS rate, we have low friction, and the surface has been removed. So the obvious intervention is to replace the high friction surfacing. And then as a secondary action, I would also consider putting in some additional signage to warn of the bus stop and the upcoming roundabout. So that was the A346 into Marlborough. The next one is the Lee Road in Westbury. So this is a really interesting one, actually. And we're looking at this section of road here. So we've got this kind of major road, which has a minor road coming in from its right, and then another minor road coming in from its left. The way that the map is drawn, it makes it look like this is a dual carriageway. It isn't. It's a very small side road going into some houses. And here we have a fairly similar story. So we have a high ABS rate, low harsh braking rate, low friction, a speed delta which is okay, but 0.66 on a... sorry, this portion of road is 30 miles an hour, so 50 kilometers an hour. So that's not too bad. And a maneuver score of 2. So what can we see from the imagery and the accident data? Well, these are the accident data. There's been 3 accidents in the last 3 years on this bit of road. And what we're looking at here is from this position looking into the road here. And this is what I think is happening in this location, is that if you're on this side of the road and you want to come out from this minor road onto this big road, so going this way, and let's say, for example, you want to turn right, which in the UK is the harder of the 2 turns, you can't see anything that's coming from this location because of this wall, which I've hidden from with the map. But you can't see anything because of that wall. And what that means is that you need to put your car as far over this line as possible. So what is probably going to happen then, anyone coming down the road this way and wanting to turn left into here is going to see you late because there's another wall here blocking their view, and they're going to be coming in at some relatively high speed on a material that doesn't have amazing friction properties. And so what's going to happen, they're going to take this corner, they're going to either understeer or oversteer, depending on the type of car that they have, and they're going to crash into the person that's waiting to turn right. This is what I think is happening. And so the interventions for this would be, again, because I'm a materials guy, we always want to be replacing surfaces, replace the surface, and just give a little bit of warning to the driver. So in the UK, there's something that we can do which is called hatching. So this means that you take some yellow paint and you form essentially a crisscross pattern on the roads. And we do this at junctions where we don't want people to stop primarily, but it's also used as a warning to say this area is a bit weird, just take it carefully here. And if you're really, really serious about this, you could consider signalizing that junction. So putting in traffic lights here to physically stop people from coming down, and also to aid people's ability here to turn right or left, as the case may be. I think that's a bit overkill in this situation, given that the accident observations here are quite low. There's only 2 more to go, don't worry. We've got Dunkirk Hill in Devizes, horrible name. So what are we looking at here? Again, we're going this way, up the hill, and there is a small side street here. This one's pretty wide, actually. High ABS rate, high harsh braking rate, also low friction, which is kind of strange. But I think that has something to do with the hill. Very high speed delta, high maneuver score, no hydroplaning. And what can we see from the imagery here? Well, firstly, there have been a couple of accidents here, but that doesn't really tell us or not. That could be just something random going on. But what is quite clear to me is that this is a blind bend. And we're going, this is the driving direction. Again, we're going up the hill. So this is a blind bend, and this is a very, very narrow street. It's also a road which has a lot of damages on it as well. So, how are we doing on time, Johan?
10 minutes, I think.
Sweet.
Yeah.
So what can we do here? Well, for me, the obvious one is just to reduce the speed limit. Again, we want to replace the surface, because we're materials guys. We always want to be replacing surfaces. There are also no road markings on this stretch of road, so they need to be replaced. And this is the most pragmatic option. Cut this bush so that people can see around the corner. Sometimes it can be as simple as that. Last one, A36, A303. This is a really special road to me. I'll explain why. My grandparents used to live just there. And exactly on this stretch of road, I had a motorcycle accident when I was at university. How about that? It wasn't for the reasons that we're going to discuss today, by the way. Poor maintenance, that was a different thing. I needed NIRA dynamics data on my bike, yeah. So what's going on here? Well, here again we have quite low friction, an enormous speed delta, 1.27. That's just ridiculous, right? And a very high maneuver score and a reasonable ABS rate. It's not enormous, but it's probably enough when you're going that fast, right? And the key thing to understand about this road is that this is a dual carriageway, but it's not a motorway. And notice that people are doing motorway speeds. It's also on a junction, so that folks are turning off on the junction.
Were you doing motorway speeds?
I was not, actually. I was doing pretty low speeds when I came off there. Yeah. Right. What does this road look like? Here we go. That's what it looks like. There's no accidents here, so this is showing us the kind of accident propensity to risk dichotomy. But what have we got in Google Images? I promise I didn't go looking for this, but there's an enormous skid mark here where somebody has had to do an emergency brake. This is where a little bit of local knowledge comes in, because one of the things that I happen to know about this bit of road is that there are 2 junctions very close together, and the A303, which is the road that intersects with this one, is another major road in the area, and the one before it is not. So often people get confused at this junction. And I also happen to know, because my grandfather was one of these people, he thought that was a motorway, which is why he would have been in that 1.27 speed delta, doing motorway speeds on a 100 km/h road. So what would I do here? Well, yes, replace surfaces there again. Good. We're going to make some more money. Right, improve the road markings to allow for better navigation. So I would do exactly what Google have done. I would put A303 signage here and A36 signage here, and make it explicit on the other junction as well. I would install explicit speed limit reminder signs. So in the UK, we have this terrible habit of using the white sign with the black mark on it, which means de-restricted, but it doesn't mean you can drive as fast as you want. People need reminding in this location that this is to 60 miles an hour or 100 kilometers an hour, so you would have a round sign with a 60 in it. What's the last one? Oh yeah, if you want to get really really aggressive with it, you could install a speed camera here. My experience though is that that would help in this location, and you would push the problem down to the next junction that shares these properties. So, thanks everyone. I guess we can go to open questions now.
Thank you very much, guys. Thank you very much.
How did we do for time? Was that all right?
It's perfect. We have about 2.5 minutes for opening questions. So if anybody here has a question they would like to discuss in the open, you're more than welcome to ask it. Yes.
Mm-hmm. Yeah, there's a reason that I'm smiling. So the question was, did we account for glare from the sun in any of this? The answer is not right now, but we think that we might be able to do that using the environmental sensors in the vehicle. So if you have a system which has automatic climate control in the vehicle, it has a sun sensor in there. So we think we might be able to use it for that purpose. And the reason that I'm smiling is because my wife said exactly the same thing to me when she looked at that image too, so you're not the only one. That's right. Exactly. I should actually go back to those accident data and see if they all occurred at a similar time. That's a very good point. Thank you. Yeah, so the question is about wildlife and if we're considering that. The answer is going to be the same. Not right now, unfortunately. We do have a problem with wildlife in the UK, but this isn't just a UK product, so I understand where the question comes from. There are options for using things like near crash data for wildlife, and I would hope that in locations where there are for example, a lot of wildlife crossings, that would be reflected in other data sets as well, like, for example, the harsh braking data set or the ABS data set. Have you given this any thought, Johan?
No, but I think, as you said, the near crash data does include information about if there was an animal that a vehicle reacted to. This would be the warn and brake assist in the modern cars now that automatically brakes when it sees an animal or pedestrian or bicyclist or whatever. But yeah, we would have to consider that because those events will be quite sparse as well, I would assume.
Yeah, yeah, possibly.
Yeah.
Please. Mm-hmm. Yeah.
Yes.
So the question was, are we collaborating with folks like VTI, which is the research arm of the Swedish Transport Authority, right? We are definitely going to be working with anybody who will be able to help us take this further, and one of the obvious places to go is research institutes like VTI.
We have a meeting with them regarding this in January.
Great.
Yeah.
Yes. So yes is the answer.
We also are in a project, or we are starting a project with VTT, which is the VTI in Finland as well.
Mm-hmm. And in the UK, we're going to be looking at partnering up with the National Roads Authority there, hopefully at some point in the future, and with the organisation that supplies them with their traffic safety data, which is IRAP. So hopefully that all works out too, but it's not a done deal. So, yeah.
Okay. That was it for Tech Tuesday today. Thank you very much for coming. Thank you very much for being here and do a wonderful presentation. So nice. Hope to see you in the new year. And I will take away from today that you need to play Dungeons of Dragons to know everything about this.
I had a campaign yesterday, actually, which was the inspiration. Yeah.
Thank you very much, guys.
All right.
Awesome job.